So we're going to pick this up right where we left off. So on the page before, we were looking at a investment. You invested $5,500, and we had talked about that times 1.12. 1 is your initial investment, and the 12 is really like you're gaining 12% in investments each year. And we're trying to find when it's going to double. Okay, so the next screen here is showing what you would see in the calculator. So you're in Y1, you've got the original function, which is that 5,500, 1.12 to the t. And then you have a couple options. What they're doing right here is using the table, and you're just kind of scrolling around trying to figure out when is our investment reaching $11,000 at doubling rate. So you see it's in between 6.1 and 6.2 years. So that gives us a roundabout. And this next picture here is what you get if you go into Y2 and put that amount that we want, that 11,000, and then find this intersection. The intersection, if you go under Calc, which is above Trace, and I think it's number 5, you go under Intersect, you can find the intersection of any two lines. So that will give us the exact one. It says it intersects at 6.12 if I round. So that's how many years it takes for that to double. So the next example we're going to look at is a decreasing one. Instead of looking at how long it takes to double, we're going to eventually look at how long it takes to cut in half. So this one actually has a lot to do with, it's just like your first project was. Okay, so you purchased a new car. And the first project was that it lost the same amount each year, so I had made it so that it was linear. Okay, so this one, this one's more practical. You lose more at the beginning, and then it kind of settles down as the car gets older. So you're losing a percentage. So it's saying that your car is depreciating by 30% each year. Okay, so notice I don't want to times each one of these numbers. If I'm looking right here, there's 22 and the 15, all these numbers, it's not times by 0.3, okay? So that's not, 0.3 is not my decay factor, okay? So to figure out my decay factor, we're going to figure out the ratio like we did in that last one. Whoops, that was a mistake there up there. To figure out what we have to actually multiply by. So determine the value that 22 is multiplied to get 15.4. So if I did 22, whoops, sorry about that. If I took the 15.4 and divided it by the 22, okay, found that ratio, I would end up getting 0.7. Okay, and likewise if I did 10.8 divided by 15.4, I would also get 0.7. So the idea is if it's losing 30% of value each year, well then it's keeping 70% of the value. So I'm multiplying each one by 0.7, and that makes it go down by 30% every year. So now we're going to fill in the table like we did for the one before, okay, writing as powers. Okay, so this right here, they filled in the first couple for us. So 0.7 to the 0 gives us our initial. Remember, it gives us our y-intercept. That right there is our A. Then this is after 1 year, 15.4. So after 2 years, this will come out to be 10.8. So that's the value that it has. Then 22 times 0.7 times 0.7 for 3 years would give us our 7.5. And likewise, after 4 years, we would do 0.74 times. So 22, our initial, times 0.7 to the 4th. So it loses 30% 4 times there, would give us 5.3 thousand. So we're going to actually write the equation for this. We have everything we need. Okay, so we know the value. I'm going to call it VFT, just so we put it in function notation. It was initially 22, and everything's in thousands here. And it's losing 30%, so it's keeping 70% of its value every year. So there's my decay factor, and there's my y-intercept. So they're having you put that into the graph. To answer the next question, we don't need that. We know the vertical intercept is going to be that A value, so it's going to be the 0.022. And what does that actually mean? That means the initial value of the car. Okay, when it was new, when t equals 0. Alright, so now this is like what we did before, but now we're going to find the half-life. How long does it take for the car to lose half of its value? So this is what we were doing on that first example in this slide, where y1, you put in the function, and then y2, put in 11,000, and you can use your table, or you can use that calc intersect to figure out where do they cross, how long does it take. Okay, and if you do that, it takes about 1.94 years. So the fact that it comes out not a whole number of years kind of leans towards using that calc intersect, because a table you're going to say it's between 1 and 2 years. It's going to be harder to narrow down. So just like before, when it took, in a previous example, it took 5.7, I don't remember if that years for the cell phones to double, and it was consistent throughout the whole function. Same thing here. So if we wanted it to have again, it's going to take the exact same. For one function, it's going to have the same half-life or double. Okay, so it remains the same, it's saying it right here, for all output, okay, for that particular function. Alright, so let's look at another one. So this one is a population in Buffalo, okay. So originally, they're looking at the first year is 1970, so that's what they're calling t equals 0. So I'm going to look at this function before I do anything with it, and I'm going to see right here is my decay factor. It's below 1. So it's not, so really this means that my population is not decreasing very fast. I'm multiplying by 0.995. Okay, so it's keeping most of its population each year, but it's going down a little bit. And then this right here is my initial. This is my A. Initial population. And that's in thousands. Okay, so first thing, let's see. You have this into a table, okay, and looking at the half, how long it takes for it to go in half. So 1102 is the initial thousands of people, half would be 551. So again, here they're using your table, just showing you another example of that. And then they're using the intersect. Okay, the second one is they have the original function in y1, and then in y2 they put in this half, which is 551, and they find that intersection point, and then you can see this is where it happens at about 138 years, 138.3, depending on how we're rounding. So that's the same thing you did above. Let's look at one more example. Okay, so this one, okay, they're giving us a little bit of background on inflation. Okay, so they give us a little thing for inflation rate in 2005 was 4%, so that means every year the cost of something is growing by 4%. So as soon as I hear that, I think I would have to times it by 1.04. That would be my growth factor. So now they're saying, and let's assume for part A, let's assume the inflation increases and remains about 5% for each decade. Okay, so it's not each year, each decade. You can calculate the cost. So originally we're saying in the first year, a pizza costs $8. And then we're going to figure out for each year over the next 10 years, what would be the price. Okay, so the first year, let's fill in, it's $8. Okay, so the second year, if I do this times, if I do 8 times 1.05, I'll get my 840. And then keep timesing by 1.05 because that's my inflation. This is growing, and this is what you get. So you could stop the video right now and calculate all these, make sure you got them, and then restart it and make sure you've got the same table I do. So I'm just going to finish this table. Okay, so now we're going to determine the function. Again, even from the beginning, we didn't even need this table. Just from right here, I could have written the function. I knew my initial price, which was 8, and I know my growth factor is 1.05. That means it's growing by 5%. Remember, the 1 is just keeping the initial cost of the pizza, and then the 0.05 is what it's growing by. I can check this function out. If I put in t equals 0, I should get the 8 out. So explain the meaning of A and B. So A is the initial cost of pizza. Okay, it's our y-intercept. And B is the growth factor. So this means that the cost is increasing by 5% each year. So use the cost function to determine the cost of a pizza after 5 years. So if we do C of 5, so at this point I can do a couple things. I could put it into my calculator. I could put y1 equals 8 times 1.05 to the t and use my table. Or I can just calculate it like this. Either one, but you kind of want to be used to doing both so you can you have multiple ways to check an answer. So 10 point, although we actually already had this on our table above too, right? Sure. So there's 3 ways I could have found it. I really already found C of 5. All right, so then they are doing this graph for us. They have that graph into y1, and they did this over negative 20 to 20 on their x's. Okay, so they're asking us, is this relevant to the original problem? So for this particular problem, we're talking about number of years and the cost of the pizza. So really, we only really care about this part of my graph. Okay, so it's not, the whole graph is not relevant. We only really care about, we only want non-negative values on the x-axis, because that's our t, that's our time, number of years. So we were resizing it. Okay, so instead of going from negative 20 to 20, we're going 0 to 20. So if we change our windows, we get a much nicer graph. I'm just going to sketch it over here on the side. We get a graph more like this. So our initial cost was 8, and then it's growing over time. So this would be t for years, and this would be cost. That's our new one. How many years will it take for the price of an $8 pizza to double? Okay, so a couple ways I can do this. Okay, so I can do my table and look for $16 as my y, as my output, or I can do calc intersect, and that would mean that I would have to have in y2, I'd have to have that 16. I'd have to have that horizontal line. Let me just add it onto the, let's just say that up here is 16. What we're looking for is that spot right there. Okay, if you find that, if you go and do one of those, a table or the intersect, I think you find it's to be, is about 14 years for the price to double. And if I want to figure out how long does it take to double again from 16 to 32, it would come out to be the same thing. Remember, it has one kind of double time for the whole function. Over here, talking about growth factor, decay factor, we talked about the doubling. Okay, the half-life, remember those are the same for once you find it once for the function, it's true for the whole thing. And the other new thing in this activity is that A value, okay? We didn't have that on the other two. Now knowing what the initial is and having that be part of our function in this form. Okay, so try some of the exercises. Practice trying to find the growth factor or decay factor from the table. Okay, that's a good way, because once you do that, you can write your entire function, you can graph it, and find anything you need.